Welcome to the world of macroscopic Casimir gravity, or MCG, a revolutionary framework that reimagines gravity as a dynamic flow of structured vacuum energy. Developed by Colonel James Hartman, MCG extends the classic Einstein gravity by introducing a new field, the Casimir structured vacuum. This field, shaped by electromagnetic environments, material phases, and turbulence, gently overlays the familiar Newtonian and Einsteinian gravity. In this video, we'll journey from the microscopic Casimir effect to planetary-scale storms and even speculative propulsion. Let's begin by understanding the core idea. Gravity isn't just about mass, it's about how the vacuum itself is sculpted by the world around us. The heart of MCG is the Casimir effect, a quantum phenomenon where closely spaced plates experience an attractive force due to changes in vacuum energy. MCG takes this microscopic effect and scales it up, proposing that similar vacuum structuring happens in storms, oceans, and even galaxies. The same mathematics that describes Casimir plates now applies to droplets, clouds, and planetary vortices. This continuity means that the vacuum field UC(xt) flows seamlessly from nanoscales to macroscales, always responding to geometry, density, and electromagnetic fields. MCG introduces a single vacuum field, UC(xt), whose behavior is determined by the effective Casimir length scale, LEF, and the material's susceptibility, chi-MCG. Whether we're talking about atomic lattices, water droplets, or storm clouds, the same formula applies. UC(xt) equals AXT, let 210FC/LEF4XT. This means that by changing geometry, density, or phase, we alter LEF, which in turn modifies the vacuum energy density and the local gravitational potential. The beauty of MCG is its universality: one field, one flow, all scales. Key innovation in MCG is the susceptibility function, chi-MCG. This parameter captures how different materials, like hydrogen, oxygen, or water, interact with the structured vacuum. For example, liquid water, with its high density and strong hydrogen bonding, has a large chi-MCG, making it heavy in Casimir gravity. In contrast, hydrogen and oxygen gases have low chi-MCG, feeling almost weightless in the MCG sense. This explains why storms and oceans, rich in water, exhibit strong MCG effects, while dry air does not. MCG doesn't replace Einstein's gravity, it gently extends it. Think of gravity as having two interacting layers: the familiar Newtonian Einstein potential, phi, sourced by mass, and the new MCG potential, phi, sourced by structured vacuum energy. The total gravitational potential is phi equals phi plus phi. In regions where the vacuum is highly structured, like storms, plasmas, or dense water columns, phi adds a fine structure to gravity and time dilation, while in ordinary conditions, Einstein's gravity dominates. One of the most intriguing predictions of MCG is structured time dilation. In the MCG framework, time dilation isn't just a function of altitude or mass, it's also shaped by the local vacuum structure. For example, inside a thunderstorm, the time dilation gradient varies from the anvil top to the tornado core, following both mass and vacuum configuration. These subtle variations, though tiny, could be measured with precise clocks, offering a new experimental window into gravity. Major thunderstorms and hurricanes are not just fluid phenomena, they're macroscopic Casimir reactors. Their mass, electromagnetic fields, turbulence, and dielectric structure combine to create complex, fluctuating boundaries in the sky. These boundaries modulate the vacuum field, forming Casimir cavities that drive strong local variations in UC. The result: storms become laboratories for observing structured gravity and time dilation in action. Tornadoes, hurricanes, and whirlpools can be viewed as rotating tubes of altered vacuum. High vorticity, density gradients, and aligned droplets or aerosols create anisotropic dielectric structures, twisting and stretching the vacuum field. In MCG, these vortices not only move air or water, they also drag and reshape the vacuum, producing unique gravitational and time dilation signatures that classical gravity cannot explain. How does water feel heavier in MCG? It's all about susceptibility. Liquid water, with its high density and strong bonding, couples strongly to the vacuum field, dragging phi with it. In contrast, hydrogen and oxygen gases barely interact with MCG. This difference is encoded in chi-MCG, allowing MCG to mathematically express the intuition that water is dense in Casimir flow, while its constituent gases are nearly weightless. Earth's spin not only shapes weather patterns through Coriolis forces, but also imprints on the vacuum field in MCG. As jet streams, ocean currents, and storm belts move, they continuously resculpt UC, creating a subtle MCG frame that can be slightly offset from the pure Einsteinian frame. Over time, this could lead to tiny corrections in Earth's rotational dynamics, all sourced by the structured vacuum. Can we test MCG? By deploying precise clocks vertically through storm regions, we can look for time dilation patterns that correlate with storm-top electric fields, ice layers, and lightning, not just altitude. Similarly, placing clocks around a tornado or ocean whirlpool could reveal azimuthal time dilation structures. Even photon frequency anomalies in glowing tornadoes might hint at MCG's influence, offering experimental pathways to validate the theory. One of MCG's boldest claims is that it can explain galactic rotation curves and gravitational lensing without invoking dark matter. In standard gravity, missing mass is attributed to invisible dark matter halos. MCG, however, replaces this with a structured vacuum field, UCX, and chi-MCGX, that provides the necessary curvature. The geometry remains Einsteinian, but the source is richer, eliminating the need for exotic dark matter particles. No dark matter theorem in MCG states, for any galaxy or cluster, if the structured vacuum field is chosen so that its effective density matches what would be attributed to dark matter, then the resulting gravitational potential and lensing are identical to standard models with dark matter. Thus, all classical dark matter phenomena can be attributed to dynamically structured vacuum, not unseen particles. This is a paradigm shift in how we interpret cosmic structure. As density and internal stress rise in a material, MCG predicts not just stronger vacuum structuring, but directionality, akin to gravitational piezoelectric effect. In dense, stressed matter, the vacuum flow can be redirected slightly off-axis, producing tiny lateral accelerations. This piezogravitational response means that internal stress can branch or squeeze the vacuum flow, subtly tilting the local weight vector without violating Einstein's gravity. Imagine a dense slab under uniaxial compression. In MCG, this stress induces a small anisotropic correction to the vacuum mass density, leading to a lateral gradient in the MCG potential. The result is a minuscule lateral acceleration, AX, signifying that internal stress can branch and squeeze the vacuum flow away from the main MCG column. While the effect is extremely small, it provides a concrete realization of the piezogravitational concept. The toy model, the main MCG flow is vertical, aligned with gravity. However, local stress and microstructure modulate the effective confinement lengths and susceptibility, making the vacuum response direction-dependent. Some regions act as vacuum sinks or sources for lateral modes, causing field lines to branch or squeeze sideways. This branching is the macroscopic manifestation of nanoscale Casimir fluctuations organized by stress. Detect piezogravitational MCG effects. A precision laboratory experiment is proposed. A dense slab or rod is suspended in a vacuum chamber and subjected to controlled stress using piezoelectric stacks or mechanical preload. The setup is mounted on an ultrasensitive torsion or beam balance with laser interferometry or optical lever readout. By modulating the stress and using lock-in detection, researchers can search for tiny lateral accelerations correlated with stress changes, potentially revealing the elusive MCG signature. Credible experiment must rule out conventional effects. This means running tests with the actuator installed but not energized, using dummy masses and applying thermal-only modulation. Rotating the test article or reversing stress direction should flip the MCG signal if it's real. Comparing different materials and microstructures helps isolate the effect, ensuring that any observed signal truly arises from piezogravitational MCG, not artifacts. Imagine a high-resolution cross-section of the experiment. A vacuum chamber houses a suspended slab with stress actuators and laser interferometer readout. Overlaid are red and orange MCG field lines bending slightly sideways through the stress specimen. A small graph shows lateral displacement versus time, highlighting a faint sinusoidal component at the modulation frequency. This visual brings the abstract theory to life. We can modulate the vacuum field in the lab. Could we scale this up for propulsion? Enter the speculative Casimir flow drive, a concept for a high-tech flying saucer that uses tunable Casimir structures and negative energy control. By engineering the vacuum field around the craft, it's possible to create directional gradients in physics, effectively tilting the local gravity vector and enabling 360-degree control without reaction mass. Casimir flow saucer is envisioned as a disc-shaped craft with sectorized Casimir flow modules embedded in the rim. Each sector contains multilayer Casimir cavities and tunable metamaterials, allowing precise control of LEF and chi-MCG. By modulating the phase and orientation of these sectors, the craft can shape the local vacuum field, creating net tilts in the MCG-induced gravity vector for omnidirectional movement. Within the saucer, arrays of Casimir cavities create localized negative energy pockets. These pockets act as wells and ridges in the structured vacuum, allowing the craft to reduce its effective weight or bias the gravitational vector. By dynamically shaping these negative energy zones, the saucer can achieve partial gravity relief and directional acceleration, all without traditional propulsion. The Casimir flow drive, the vacuum is treated as a controllable medium. The craft's metamaterials and field drivers act like pumps and vanes, reconfiguring the mode density and vacuum stress around the hull. This creates streamlines of MCG flow, similar to how a wing shapes airflow. The result is a field shell around the saucer, with asymmetric vacuum structure producing net curvature imbalances and effective thrust. Speculative Casimir flow saucer would require advanced technology, nanostructured metamaterials with tunable LEF, high-voltage field drivers, quantum metrology for real-time monitoring of fight gradients, and AI-driven field modulation for stability. These systems work together to maintain balance, shape the MCG flow, and enable translation, rotation, and hovering, all by manipulating the structured vacuum. Visualize a top and side view of the saucer hull, with radial sectors highlighted. Each sector contains Casimir cavity stacks and field driver blocks. Overlaid are vacuum flow lines showing an asymmetric MCG field, denser on one side, lighter on the other. Equations for Fick and a schematic MCG thrust vector complete the scene, illustrating the core propulsion concept. Cross-sectional view shows the saucer at the center, surrounded by shaded negative energy shells and normal vacuum regions. Vector diagrams illustrate local, effective down vectors tilted toward the intended direction of motion. Inset time dilation contours reveal small asymmetries, highlighting how the craft manipulates gravity and time through structured vacuum engineering. This poster juxtaposes the laboratory experiment, a slab under stress, torsion balance, and tiny lateral MCG acceleration, with the saucer in flight, showing sectorized modules and 360-degree field control. The caption reads, "From stress matter modulating vacuum structure, lab scale, to engineered Casimir flow shells, craft scale." It visually connects foundational science to speculative technology. The unifying power of MCG is its continuity. From microscopic Casimir plates and molecules to droplets, storms, and planetary vortices, the same vacuum field and susceptibility gradients apply. This single flow ties together gravity, time dilation, and even the possibility of advanced propulsion, all within one mathematical and conceptual framework. CG opens new frontiers for both experiment and theory. Precision laboratory tests of piezo gravitational effects could validate the theory at small scales, while astronomical observations may reveal MCG's role in galactic dynamics. Meanwhile, speculative engineering pushes the boundaries of what's possible, imagining craft that ride the structured vacuum itself. The journey from Casimir plates to flying saucers is just beginning. Macroscopic Casimir Gravity offers a new lens on the universe, blending quantum vacuum structure with classical gravity. It promises not only to explain phenomena from storms to galaxies without dark matter, but also to inspire new technologies, perhaps even gravity control and advanced propulsion. As research continues, MCG stands as a testament to the power of unified, scale-bridging physics, inviting us to rethink the very fabric of reality.